The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
All right, now let's shift our attention towards quantum numbers. In a nutshell, quantum numbers are going to be telling us, they're going to describe in detail the characteristics of electrons in atoms. And once we understand quantum numbers, that's going to help us develop a deeper understanding for the electron configuration for multi-electron atoms. And that's what we're working towards. Now, exactly what do quantum numbers tell us? They're going to describe the energy of an electron and the most probable distance of an electron from the nucleus, as it says here, and that'll be demonstrated through the first quantum number. Secondly, it's going to describe the shape of the orbital. And if we take a look over here at figure 1, the orbitals that we'll be taking a look at is the s, p, d, and f orbital. The s orbital is spherical, the p orbitals are more dumbbell shaped, and the shapes become more complex as we go on. And we'll take a look at the shapes of orbitals at the latter part of this lecture series. Thirdly, they're going to describe the position of an orbital, and if looking over here at figure 1, what we mean by the position of an orbital, we're talking about the spatial orientation of an orbital, right, in the space around the nucleus of an atom along the ordered set of coordinate axes. And lastly, we'll be taking a look at the spin, the fourth quantum number. That's going to give us the spin of the electron, which is either going to be spin up or spin down. Now, once we obtain all this information for the quantum numbers, a conclusion by the end of this lecture that we'll be able to draw is that no two electrons are going to have the same quantum number. Thus, each electron in an atom is going to be accounted for by a set of exclusive quantum numbers. And that's pretty remarkable if you think about it, because that tells us then that each electron has its own unique quantum address. Okay, great. Let's get started here and take a look at the first quantum number. Now, before we read our definition here, once again, the first quantum number is going to be telling us about which energy level the electron is in around the nucleus. In other words, the most probable distance of the electron from the nucleus. Now, reading our definition here, it says principal quantum number. That's going to be given by n, is a positive integer which describes the relative size and energy level or shell of the orbital. Now, when n equals 1, that's the first energy level. When n equals 2, that's the second energy level. When n equals 3, that's the third energy level. And as n gets larger, that's telling us that the electrons are going to be getting farther from the nucleus. Furthermore, as n gets larger, the orbital size is also going to be increasing. And what I mean by that is an s orbital, if we take an s orbital, for example, that in the second energy level, right, that will be larger than an s orbital in the first energy level. And thirdly, as n increases, so do the size of the atoms as well. And we'll see an example of that shortly. Now, n, if we want to find the total number of orbitals, as it says here, we can do so by squaring n, right? N squared equals the total number of orbitals, and we'll do an example on a subsequent slide. And n can be any positive integer, right? Can be any value, any positive integer beginning at 1, as we see here. Okay, great. Let's continue our discussion now on the next slide. Now, what other information can we obtain from the principal quantum number? For one, if we